Hey everyone, so I want to talk a little bit about motion graphs in this class. Motion graphs are an extremely important aspect that you need to be able to do. So just jumping right into it, let's say that we had a displacement graph. One of the things that you need to know is what do we get when we take the slope? Because remember, anytime we have a graph, your mind should immediately go to how can I find the slope, or should I find the slope, should I find the area? You need to know what you end up getting when you do both of those. Now, most of the time you're going to use an equation to figure that out, but for motion graphs in particular, you kind of have to understand the relationship between all three different motion graphs. This might become a lot easier if you've taken a calculus class or a pre-calc class. You might naturally know what you get when you take the slope or an area of one of these, but if in case you don't, just kind of have to get practice. There's a few different ways to go about it, so I'll go through that. So let's say we had this set of data and want to know what do we get when we take the slope of the displacement graph. Well, let's actually plot this out. So I plot it onto my graph. I get a linear line. The slope is change in y over change in x. So I pick 2 points. I could pick the 10 and 0, 5 and 0. Do change in y, so 10 minus 0 meters divided by change in x, 5 minus 0 seconds, and you end up getting 2 meters per second. Note meters per second. That basically means that the slope of the displacement ends up being a velocity. So once we have a displacement graph, if we find the slope, we get the velocity. So if you end up forgetting this, you can always just do the slope and see what your units get you. Because this displacement graph is a linear line, what we say is that it has a constant slope. Because it has a constant slope, that tells me that my velocity also has to be constant. So this is one thing that you're going to have to try to get a handle of is making sure to differentiate what the graph is doing versus what the slope is doing. So the displacement graph is increasing, but the slope is constant. So they're two different things, and you want to kind of keep track of that. And a lot of times, to make life easy, you could just try to get into the habit of replacing the word slope for your displacement graph as with the word velocity. So if you're looking at this graph and you say, oh, the slope is constant, you can also infer that the velocity is constant because they're synonymous here. So a linear graph, taking the slope of that gives us a constant graph. Now, one thing that we want to know is what if we were given the velocity graph? Is there any way to get information about the displacement? What is essentially the opposite of this? Like I said, if you know calculus, you might know the fancy way of this. You might actually know that the fancy word for slope is called derivative. And the fancy word for the opposite of a derivative is called the integral. Now, in layman terms, what we say is that is the area. So let's actually check this out. Now, we can see this through the equation. If we reorganize that average velocity equation, the one that's v bar equals d over t, and instead write it as d equals vt, I can see that if I multiply velocity and time, I get distance. Well, if my velocity graph looks like this, the only way that I can multiply them is by turning this into a shape like a rectangle and doing length times width. So the area gives us the displacement. So to answer the question, what's the opposite of slope? That's the area. So if taking the slope brings us one way in the motion graphs, taking the area will bring us back. So slope of displacement is velocity, the area of velocity is displacement. Now let's look at another displacement graph. Let's say we had this, what would the velocity graph look like? Again, because of the concept of slope, velocity for a displacement graph is related to the slope. So I would look at it, the slope is constant, therefore, the slope is constant and zero, therefore the velocity graph is constant and zero. All right, so for each of these segments, determine the velocity of the object. Pause the video, work yourself, we'll go in a second. All right, so all we have to do is just look at each of these four segments. So in this first segment, it goes from 0 to 6. So when we take the slope of this line, we end up getting 50 meters per second. In segment 2, it doesn't really change. It just stays 6 the entire time. So the slope of that will end up being 0. In the next segment, we take the slope of that again. We get 2.5. And in the last segment, we get negative 17.5. Like I said, it's important that you avoid using the equations like d over t or the annoying x. In some cases, it can work, but you might end up having issues. You might have to be very careful with it. For example, if you're doing this section, if you just get into the habit of doing d over t, you might accidentally say, okay, let me do 6 divided by 0.6 to find the speed. Doesn't work that way. Like I said, you have to do the slope of the line. So anytime you're looking at a graph, what's the slope? What's the area? Once you have a displacement graph, and now that we know how to get a velocity graph from it, we can actually rework this graph so that it represents velocity. So what we would do is, section off the different parts and look at each piece individually. So in the first part, we already said that slope is constant, therefore the velocity graph is constant, and we already know it's 15 meters per second. That second segment, again, constant and 0. So I put that there. The next one, it's constant with 2.5. And the last one is negative 17.5. So this is what my graph ends up looking like. It's kind of like a step type pattern. But as long as you kind of get the idea of how to go from one graph to the other, that's all that really matters. All right, so here's another question. Pause the video, work itself, and we'll go over in a second. All right, so going back to this. Now this graph, this question is saying, in which of the following is the displacement constant? So the displacement being constant means it looks like this. That is a constant displacement. Because it's constant, it's not changing. All right, so the slope, not only is it not changing, it's 0. There is no slope to this line. So the slope of this graph is 0. And as we mentioned before, slope for a displacement graph can be replaced with the word velocity. So when I say the slope is 0, I also mean the velocity is 0. So of these three choices, none of them have a 0 velocity. So this was a little bit of a trick question. Again, trying to make you realize not to confuse the idea of what the graph is doing versus what the slope is doing. All right, so let's actually show how we can actually get the displacement graph from the velocity graph. Now this one's a little bit trickier. If you know an equation, you could always take the integral, like I said, but if you needed to do it freehand, what you would normally do is actually take the area, but you'd have to take it in little segments. So you'd have to do a segment like this. That's a rectangle, so the area is base times height. Plug in the numbers, we get 1.2. So by the time the displacement graph gets to 2 seconds, it goes up to 1.2 meters. We go to another section, again, changing the base again to 4 seconds, we get 2.4. So again, our graph goes all the way up to 2.4. Keep going. Take the area again, we get that by 6 seconds it's 3.6, and we just keep doing this, and we end up getting a line. Now, because the velocity graph was constant and our displacement graph was going to become linear, we didn't really have to go, that much in detail, because all we would need to know is where it starts and then where it ends, and then just draw a line between those 2 points. But for a graph like this, it does become important, because here, now the shape I have to make is a triangle. The area of a triangle is base times height. Plug it in, and I get that my displacement goes up to 1 meter. Go to 4 meters, 4 seconds, sorry. Plug the numbers in, and it goes up to 4 meters. So we can already see that it kind of jumps up. Go to 6, goes up to 10.5. My graph makes a mistake. It should go up to about here, so the graph actually should look like this. And you can keep doing this, but you'll notice that the bigger the intervals that I do, the more angular it looks, the less smooth the curve looks. So if you want a really good smooth graph, what you'd have to do is do very small intervals. But really, the whole point of this is just to get a nice idea of what the graph should look like and realize, okay, it's a curved graph, not a linear graph. So yeah, once again, if we have a linear velocity, then that means our displacement graph is exponential. And that also works the other way. If our displacement graph is exponential, taking the slope of that gets us a linear graph. So is there easier ways to find slopes? Yeah. A lot of times you don't actually have to do any calculations for curved graphs finding the slope because it's not really important. Like I said, to find the slope, you kind of do need calculus for a curved graph. But instead, what you want to actually be able to do is understand, is the slope going 0, positive, or negative? Those are the three things that you kind of want to be able to figure out. So the easiest way to do this is to use your hand and put it tangent to the curve. As you know, that's what the slope is. The slope is a line that goes tangent to the curve at some point. So your hand will indicate the direction of the slope. If your fingers are pointing up, the slope is positive. If the fingers point down, the slope is negative. And if your hand is flat, then it's 0. So what you can do is you trace along the graph looking at what's your direction your fingers go, and that's going to tell you whether the slope is increasing or decreasing. Because again, the point is not to know what the graph is doing, it's what to know what the slope is doing. So if we look here, your hand will start pointed downwards. As you go here, that slope will start to become less and less steep until it gets to this point where it's flat. Then it starts going up and it gets more and more up. So it starts negative, goes to 0, and then becomes positive. Now, if I want to make a velocity graph, I would want to make sure that I show this, that it starts negative, goes to 0, and becomes positive. And I already know that since I have an exponential graph like this, the slope graph, in this case if we're talking about velocity, should be linear. So I'm going to make a line that goes from negative to 0 to positive. So again, that's all I'm doing, just getting an idea that this graph and this graph are synonymous if we're talking about distance and time and velocity versus time. Same thing here. If we have this graph, in the beginning our fingers are pointed upwards, so it's pointed positive. Then as I continue on, my hand slowly stops becoming steep, flattens out to 0. And then by the time I go down, my fingers start pointing more and more downwards into the negative direction. So again, my slope graph, if I want to talk about velocity, would start positive, go 0, and then go to negative. And again, linear line. The nice thing about this is that for the most part, it's pretty much the same thing because there's really only two types of curved graphs, these two. But you might see different versions of it. Maybe you see a graph where the displacement graph looks like this, where it starts at this max point and goes down. It's still a parabolic equation, but we're starting at a different location. So my velocity graph will start here in that same type of scenario. So if you shift the displacement graph over a bit so that the I guess the starting point changes, then the same thing happens to velocity. Like what I'm trying to get at is that the shapes of these graphs don't change. They end up staying the same relative to each other. All right. So now my next question is, what do I get when I take the slope of velocity? Well, I can kind of do the same thing. We can look at the units by doing the slope. Once again, slope is change in y over change in x. The y-axis this time is meters per second. The x-axis is seconds. So taking the slope gets us meters per second per second, which is another way of saying meters per second squared, which is the units of acceleration. So the slope of velocity gets us acceleration. And once again, as we said before, what brings us back down? The opposite of slope is area. So this is one thing that you can, there's a few different ways that you can remember this. Like I said, one way is just to do it, take the slope, see what you get. You can also look at units. So displacement is measured in meters, velocity is meters per second, and acceleration is meters per second squared. And as you continue, it will just keep adding on seconds. In this class, we're stopping at acceleration, but in later physics classes, maybe in college, you might actually deal with higher levels above acceleration. In that case, you'd be talking about something called jerk, and then there's the snap, the crackle, and the pop. There are a few things that you need to know about motion graphs. One thing that really kind of helps is to know is to remember the motion of the graphs, or the order of the motion. So as I mentioned, this idea that when you take the slope, you go from displacement, velocity, acceleration. Easy to remember because it follows the units. Meters, then meters per second, then meters per second squared. There's a pattern. You could also remember the area one, but that doesn't really help too much. The other thing that I recommend is remembering the order of graph types. So in this class, there's 4 different types of graphs: curved graphs, linear graphs, constant graphs, and zero graphs. So one thing that you can do is if you kind of forget what the shapes should look like, you can use this order and this order in order to figure out what the graph should look like. So if we know that our displacement graph is curved, then because the slope of displacement is velocity, I know that the slope of a curve is linear, so this should be my velocity and this should be my acceleration. On the flip side, if I know my displacement's linear, then again, following the order, the graph to the right of this is my velocity and the right of that is acceleration. So I could do this to kind of get an idea of what the graph should look like. It doesn't tell me whether it's linear up or down, positive or negative, but it does tell me that it is linear. So here's the next question. Pause the video, work itself, and we'll go over in a second. So as I mentioned there, with the order of the graphs, when you place it in, it's always going to the next one over. Now, what that kind of means is that it is impossible to have a graph where the displacement and the velocity are the same shape. So anytime you see this, where both displacement and velocity, or velocity and acceleration, or whatever, are both linear, or both constant, or both curved, it's thrown out. The only time it will ever both be curved is if you have a changing acceleration, which again is not really used in this class. So we just need to see which one of these follows the pattern that we saw, and also the fact that the slope of the displacement is reflected by the graph. So here we can see that the slope changes. It goes from positive to 0 to negative. That's not happening here, so this is thrown out. This slope is constant. This graph is constant. So far, so good. This slope is positive. This graph is negative. That's wrong. So it turns out this is my actual answer. My curved graph starts at 0 and becomes positive. My velocity graph starts at 0 and becomes positive. Here's the next question. Pause the video, work itself, and we'll move over in a second. So this one's easy. We have a displacement graph, and then looking for displacement, we just read the graph. Our graph starts at 0. Our graph ends at 0. Our displacement 0. Easy peasy. Here's the next question. Pause the video, work itself, and we'll move over in a second. Alright, so we want to know which areas is the car motionless, moving with a constant non-zero speed, and accelerating. So motionless, basically the displacement doesn't change. That's C to D. Moving with a constant non-zero speed, the slopes have to be constant, so that's a linear line. That's at BC and DE. And then the accelerating, for displacement graph, that's represented by a curve. So accelerating would be AB. All right, here's the next question. Pause the video, work itself. I'll go over in a second. All right, so this question is actually another trick one. So if we look at this, from what we know, this this displacement graph has a constant slope. Therefore, the velocity is constant. And that means that my acceleration has to be 0. This graph, my velocity is 0 and also doesn't change. Therefore, my acceleration also is 0. This one's the only one where the velocity is increasing, which means that I have an acceleration that is positive, or at least some number. So you might think that the answer has to be 3. But if you notice, none of these choices includes 3 in it, except for this. That's actually because this is the answer. The trick here was that I just said that the acceleration was constant, not that it has an acceleration. Even though these two graphs don't have an acceleration, their acceleration doesn't change. Therefore, it falls in that same category of technically being constant. So typically, if they did want 3 as the graph, they'd have to include the phrase non-zero. So which of the following is the particle's acceleration? Actually, it would be put here. Acceleration non-zero and constant. So that would pretty much hint that it's this. But because they didn't include that, it means that a 0 acceleration also falls in that same category. And here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So once again, when we have these motion graphs, the first thing we want to ask ourselves is, do we take the slope? Do we take the area? So again, looking at this graph, this is the velocity graph. They're looking for distance. That means I want to do the area. So I have a shape. I can make a triangle from this. I can also make a rectangle from this. So the area will be the combination of the area of a triangle plus the area of a rectangle. If I do this, the area of my triangle has a base of 4 and a height of 10. My rectangle has a base of 2 and a height of 10. So plugging those numbers in, I get that the area is 40. 20 for the triangle, 20 for the rectangle. For number 20, for the acceleration, again, am I taking the slope or area? Well, the answer is slope. So I'm taking the slope of this later line segment. So slope is change in y over change in x. If I look at this, looking at the first and last point, the change is 0 and it over 2 seconds. So my slope or my acceleration is going to be 0 meters per second squared. All right, here's the next question. Pause the video, work itself, and we'll go in a second. All right. Now in all these questions, I kept stressing that you're not supposed to be using equations. You're not supposed to be using timeless acceleration equation, the annoying x. While many times you can get away with it, it doesn't work all the time, or it only works if you're very, very careful. This is one of the few times where if you tried to do a slope, it wouldn't work. Because they explicitly say the word average speed, that idea of don't use an equation gets thrown out the window. You are immediately allowed to use the equation. Note this tilde is supposed to be the v bar. I just couldn't find that symbol. So we have v bar equals d over t. Plug the numbers in. So at 4 seconds, the distance is 2. So 2 meters divided by 4 seconds gets us an average speed of 0.5 meters per second. Right. Here's the next question. Pause the video, work itself, and we'll go in a second. All right. So what we end up having is a bunch of graphs that we have to draw. We're going to take it bit by bit. The first one that I want to draw is the hair. So the hair is a constant 25 meters per second. That's easy, so the velocity graph should just be flat. Next, we start drawing the cheetah. So it says that for the first few seconds, the cheetah doesn't move. So I draw a 0 line. Then for the next 20 seconds, it accelerates to a top speed. So what I can do is just find the top speed, put it in after 20 seconds, and draw a line. And that will be a linear line. Then it maintains that constant speed, so I should have a flat line at the 45. And then it goes down all the way to 0 at some acceleration rate. So if I'm graphing this, I can actually just go down 6 meters per second every single time until I reach the final end. And this is what my graph ends up looking like. Now, I didn't make the acceleration graph, but that's pretty straightforward. For the hare, the acceleration graph would end up just being 0 the whole time. For the cheetah, it'll be 0. Then it would go up for about 20 seconds, equal to whatever the slope of this line is. Then it would go back to 0 for a bit, and then go down to -6 meters per second squared. So this is what the graph would look like. Again, it would look a little bit step-like. 0, then it jumps up, flat, jumps down, flat, jumps down, flat. Now, the next thing that I want to point out, this is just something that I always really enjoy, is how everything gets connected. So we can actually get a lot of the kinematics equations from the graphs. So let's look at this graph of velocity versus time. This is a linear graph, so what's the equation of a line? It's y equals mx plus b. Now on the y-axis, I have velocity. So y can be replaced with a v. The m represents the slope. We know that the slope of the line gets me acceleration. So slope can be replaced with a. The x is represented by the x-axis, which is time. So this will be t. And b is our y-intercept, which is the point where it starts. This is what we would call the initial velocity. So what I can do is plug the variables for each of these parts, the y, the m, the x, and the b, what they represent, and I get v equals at plus v naught. Well, that's the acceleration equation, written slightly differently, but it's exactly equal to this. So we can already see that this equation is an equation of a line for constant acceleration. All right, now we have this graph, displacement versus time. Once again, it's a little curve, so we know that what is the equation for a parabolic curve? That's y equals ax squared plus bx plus c. Now this one's going to be a little bit tougher, since it's not super clear right off the bat what a, b, and c should be. So let's just start off in general. Once again, y is going to be what's on the y-axis. I'm going to use x. So y can be replaced with an x to represent position. The x's are representing the time. So the t will go here, the t will go there. And c is the y-intercept again. Because this is position, this represents the initial position. So I can rewrite this, plugging in that stuff, as the final position is equal to some number times t squared plus some number times t plus the initial position. This looks very similar to x equals 1/2 at squared plus v naught t plus x naught, obviously written a little bit differently. So we end up getting the annoying x equation. And we can already see that, how similar this equation is to a quadratic. So once again, this equation directly relates what a quadratic equation for displacement should look like. And the last one, we have this displacement graph. So now we're moving at a constant speed. Once again, it's a line, so y equals mx plus b. That again, the x is the y-axis is the position, the x-axis is time, the slope is velocity, the initial position's the y-intercept. So we get x equals vt plus x naught. At first, you may not think that we have an equation, but once again, this is the annoying x equation, except the whole 1/2 at squared gets dropped out because, as I mentioned before, this is moving at a constant speed, therefore no acceleration. So yeah, it turns out that these kinematics equations directly relate to the graphs that we draw. The only one that we don't really get from this is the timeless equation, the vf squared equals vi squared plus 2ad. However, that actually comes about from combining the acceleration equation with the annoying x equation together. So you can actually fool around and see how that works out as well. But that's pretty much it for graphs. Like I said, the main thing to take away from this is to try to get into the habit of looking at a graph and immediately asking yourself, do I take the slope? Do I take the area? And what do I get? And then, like I said, trying to differentiate what the graph is doing and what the slope is doing. And again, trying to get into that habit of looking at a graph and saying, okay, based off of this, the slope is doing blank. If you can get into the habit of doing all that stuff, and if you can master it, these motion graphs will end up being a piece of cake. That's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.